Um, in going through the movies and trying to coordinate, what's what and make notes to ourselves and everything. If you put a slide number on each slide, that's pretty useful because we can, in our comments, we can refer back to a slide specifically. Right now, I'm referring back to usually a minute and a second of the movie and say at this slide, and then that's the timing. But if you could put a slide number somewhere we can always see it is good. The other thing that is missing in a lot of presentations is when you take graphics from a paper or a textbook or online, put an attribution, you have to attribute where that came from on the slide. It's very useful for people to go back and look at the whole publication that you used. I was looking at some of the MATLAB code and sometimes it's just one image you're operating on. You want to upload that image too, right? So that when you run the MATLAB code, you can see the actual image. If you're working with tons of data, well, you don't have to upload tons of data. Okay, I know some people had hundreds and hundreds of cases. The other thing is you need to check the fidelity of your recording. So you can just go through a 4x or whatever and make sure the thing worked all the way through. Because a couple of teams, I looked at the graphics and I think, I don't think this came through the graphics, or the slides just disappeared and it was just people talking and things like that. So just give it a quick check. And while you're explaining things in the movie, it's ideal if you have a cursor that works, right? Like a laser pointer or an arrow. And then when you're explaining things or explaining data, you can focus the attention of the viewer on that stuff. That takes you to a next level of understanding when things are being explained, right? So I would highly recommend that you do that as well. Okay, so we're gonna get started. I'm going to move this down slightly so I can see it better under here. Okay, so I have the movie and we have oh, wait a minute, that's Chrome. I'm going to go in here. And now we have the summary slide. Okay, for this is group 5. And I'm going to try and get my stuff out of here. Let's put that away. There we go. Okay, so group 5, if you want to kick us off, that would be terrific. I'm assuming you're out there.
Hello.
Okay. Do we
Hello,
have
everyone.
do we have people from group 5 here?
Yes.
Can
Okay,
everybody hear me?
terrific. So you can give us a 1 minute um, introduction of the topic you did and the major results that you found. And we'll start the questions.
Okay. Hello, everyone. We're group 5, and in our project, we discussed about how photo counting CT can differ from the traditional CT. So first, I started with reviewing briefly how CT imaging works and why does the detector technology matter in CT. And then I moved on to explaining about how conventional CT's detector works and the limitations about the conventional CT's detectors as known as energy integrating detectors.
Then I went ahead and kind of described how photon CT counting works. So for each absorbed X-ray, it releases a charge in the semiconductor, which then produces a brief current pulse that encodes some of the photon's energy and timing. This integrated circuit that's below each pixel then amplifies and shapes that pulse in particular ways, which allows for filtering the noise and also managing the overlap and recovery between events. So then by processing each interaction locally and in real time, the detector can then preserve spectral detail and accuracy, even at near real-time counts, which then enables generation of data sets with much more information in the sample than traditional CT.
Great.
I'm gonna try to annotate. Hopefully it works. If it doesn't, then y'all can let me know.
Check.
So this is the summary of key differences. These were the results that we found based on our research. So first, in terms of signal type, EIDCT measures the sum of all photon energies, whereas photon counting CT detects the individual photon counts, so that gives you more detailed energy information. And then the next thing we covered was noise, and we found that EID um, systems are usually affected by electronic noise and are scatter weighted, while PCCT minimizes electronic noise and improving image clarity, especially at low doses. And so when it comes to spatial resolution, EID is also limited by the scintillator thickness and pixel size. And photon counting uses smaller effective pixels, which gives you a finer resolution. So um, PCCT is definitely like more advantageous in terms of like quality for the person looking at the data. Um, and also, EID-CT offers no energy discrimination. It treats all the photons that pass through the detector equally, but PCCT can distinguish the energy of the photon events, which enables better material differentiation. And then in terms of clinical availability, EID-CT is more widely established, and it's also a lot more cheaper, which we also went over in the video. Um, than PCCT because PCCT is more of an emerging technology. It was only like FDA cleared in 2021, and it's millions of dollars more expensive simply because of the semiconductor um, technology that is a part of it. So these were the summary of the key differences. And um, again, just to summarize one last time, PCCT is just overall more advantageous to use to analyze data.
Great. I have a couple of comments and questions to at the beginning, just from the chart here. One is when you say energy discrimination in the energy integrating detector, there's no discrimination. That does not mean that you can't make images with, integrating detectors that have different sensitivity to energy. And that is do you know how it's done on those machines? If I wanted a an image of, high energy photons versus low energy photons, how do I do that on a machine we have in the lab already?
I wouldn't be too sure on the precise mechanism, but I could infer that you could probably measure the intensity of the light that you're receiving at the I guess photodetector in the CT system. And then you could probably discriminate based on that. But you would be also introducing some other more conflating factors, such as scattering within the tissue, or not the tissue, the detector itself, as well as like how much of that light you're really going to be receiving at like the quantum efficiency at the detector.
So the way you do it, I'll give you the answer, unless anyone wants to take another shot. So basically, we talked about this. You take two images, okay? And your X-ray source for one image has a maximum of, say, 80 kVp, right? So there's no X-rays in there above 80 kVp. So you know they're not there. So when you take that picture, you have a average energy of the multispectral beam, right? That is down at, say, 48 kVp or something like that. And then you take a second image at 120 kVp, and now you have high energy photons going through the patient, and so you get a different picture, right? You get a high energy picture. So you have done energy discrimination through that mechanism. There's another system Philips has that has a stacked detector, one detector on the top, one detector on the right below it, and the one on the top is much better at getting all of the low energy photons, and the one on the bottom gets the high energy photons. And so you have energy integrating detectors in both levels, but this one picks off the low energy photons, and this one basically, cleans up the high energy photons that got through. So you can do energy discrimination. It's not as good, right? I mean, with PCCT, you can make up to like 4 or 5 bins of energy and put your photons there. So the question really is like, is it worth the cost to go to PCCT? Are there things that are occurring that we can't get with the energy integrating detector? Unique things. So let me get a couple of questions from the crowd here. This is an interesting one. Could hybrid systems combining photon counting and energy integration offer an advantage?
Think about that for a moment.
Yeah. That's why I picked it. It's like, oh, really? Yeah. I've never really thought about it that much. Um, okay, let's while you think about that in the background, we'll just do
Yes, yes.
a more technical one. Um, what quantitative metrics can be used to decide between EID and PCCT on a per case basis? How can differences in energy discrimination and noise reduction effects be measured so that radiologists can make an adequate decision on which scanner to use for specific patients? So this is a real clinical problem that we've got right now. We have one of these very expensive CTs down, in the new outpatient center, and we have everything else is energy integrating. So who do you put on the PCCT is the question, I guess.
So I guess from the engineering perspective on this particular issue, um, the way you could probably discriminate between which one would be a more effective technology for your use case would be take into large consideration your photon flux, your necessary photon flux for acquiring a good contrast in your image, right? So if you consider like the possibility of pulse pileup, for example, inside of the PCCT system, of which is going to come down to your specs of the integrated circuit that's below each pixel, and whether or not you're going to be in that dead time window at that particular photon flux could be a major consideration. So since EIDCT is much more developed technology, we have a much stronger understanding of what the limitations are on like a material basis, for example. And so there's definitely a mathematical approach there at the signal processing level where you may not be able to discriminate a certain number of photons coming through the patient.
Cool. So here's another one. When discussing pulse pileup, you mentioned that having reasonably strong bias field helps to mitigate the pulse pileup. Can you elaborate a bit more on what you mean by reasonably strong? Are there limits to how strong that field can be before causing a breakdown or some kind of leakage? So I'm going to let's go to
If you
your,
pull up slide 10, I think it should be like physical principle.
this guy.
Yes. Debating if that's the right one.
So this is the PCCT. These are the electrons. Maybe you could just quickly describe what pulse pileup is and why cranking the voltage would reduce it.
Yes. So this bias voltage that we're describing is between the cathode and the pixelated anodes in the diagram that's provided.
Right here and here.
Now, yes, when these charges are generated inside the semiconductor, they exist for a period of time, like within the material.
Right
So
here.
they're sitting there, or kind of like a physical object you could almost think of. And they have to clear the detector by moving to the cathode and the anode in order to reset the system. So if you can increase the strength of the field there, you're going to observe that there's going to be a faster clearance across the detector. So it resets faster, so to speak.
Got it.
Now, pulse pileup is a function of how quickly the photons are coming in. So if you move to slide 12, so it's like two more after this one, counting at speed. One more, I
This
think.
guy?
Yes. So there's a nice video here, actually, if you can
Sure.
play it. If two photons deposit energy in a sufficiently short interval, their charge clouds may temporally overlap on that pixel. The front end.
I just
This
turned on
guy's
the
stealing my explanation.
Yeah. Who's that guy?
um, So if you can clear it faster, you're going to essentially be having less of this pileup phenomenon that I'm modeling here in this bottom graph, because there's going to be less window for these photons to be arriving within the same span. So the detector resets fast enough that they can be discriminated as separate events,
I see.
with more bias field.
So are we talking about the width of this little pulse here?
Yes, but at dictated by the semiconductor architecture.
Right. So if I crank the voltage, right, this is the voltage of the pulse hitting the detector, right? So, but if I crank the voltage between the anode and the cathode, you're saying the width of this line gets narrower? Is that what we're saying?
That is my understanding, assuming all the other electronics function ideally.
Cool. Cool.
So is this, I have a follow-up question. Is this a simulation you guys did, or is this something you got from on the internet?
So that one I modeled very quickly in Python. There's definitely better ways that you could represent it with like wider, I want to say like wider pulses, but this seemed to work okay. But
Okay.
yes, I made this one. I can talk about how that was constructed if you like.
Yeah, well, I don't think you guys uploaded your code for this, did you? I didn't see the code uploaded.
I don't believe so. These are mostly like demonstrative graphs, so they weren't really like the product, so to speak.
Okay. So I mean, it would be helpful for you to any work you've done simulating things, to upload the code, so we can look at it.
Mhm. Got it.
All right, cool. Thanks. I think in order to stay on time, it's amazing. Even when we don't present the whole project, we go over time. Um, that's great. Thank you, Matthew, for your explanations there. And I think we're going to have to move on, though, to the next team. Okay. So the next team is team three. Okay. Group three. And we're looking at comparative study of parallel beam and fan beam.
Um, Hi everyone. So our project focuses on comparing parallel beam and fan beam CT geometries in terms of their data acquisition and image reconstruction. At the top, you can see geometric setup. The fan beam CT uses a diverging ray geometry where all rays originate from a single focal point. But in parallel CT, they use parallel rays across all projection angles. And this difference in geometry directly affects how projection data are collected and mapped into sinograms. And at the bottom, we can see we have generated these two sinograms. The fan beam sinogram show the characteristic curved patterns due to angular spread of rays, whereas in parallel, it's more linear and uniform. And on the right, you can see the reconstructed images, which demonstrate how sampling and angular coverage influence image quality. The top image shows a well-constructed Shep-Logan phantom, while in the middle and the bottom, it shows the degradation under sampling and limited angle conditions, leading to blurred images and streak artifacts. So overall, our study highlights the parallel beam geometry offers conceptually simplicity and easier reconstruction. But fan beam CT is more efficient when it comes to clinical scanners, providing faster acquisition with fewer projections.
Okay. Um, we can leave this on here. Let's start with a couple of questions. So, you emphasize the central slice theorem and show that reduced angular sampling leads to blurring streaking. Could a non-uniform angle schedule, i.e., denser sampling where object anisotropy is expected, plus frequency selective filtering outperform just doing uniform 1 degree steps with Ramlock in both resolution and noise power spectrum, which is kind of a next level thing, but just let's think about that. So this is the basic question is like, can you do a low dose scan by changing your sampling rate or sampling pattern and still recover a good picture? Anybody want to try and take that one?
Oh, I'm sorry about that. So the question is, can we do a low dose scan and we still recover the better picture? I think it depends on the case that we are studying. If the patient, let's say, has implants, let's say some metal rods or something present in the uh, slice that we are taking the image of, that would be very, very difficult, especially if we have less reconstructed data and we try to do inverse transform from that. And apart, reduced number of projections does lead to lower dose, but combining with iterative reconstructions or like frequency selective filters, it might control noise and streaks, but this is essentially a dose optimized CT scan. So uh, practically, I mean, intuitively, I don't think so we can, but if we do figure out an algorithm to do that, especially using the filters that we have, the Ramblack filters and the other such filters, uh, it's difficult to do that, but I would say it's not completely a 0% chance, because directional anisotropy is something that even the modern cities are struggling with. So yeah, strategically yes, but practically a bit difficult, especially if the patient has some kind of uh, metal rods or some artifacts present.
Right. No, I think you're on the right track there. I think if you know what the image is ahead of time, then you can design sampling schemes which optimize getting data to reconstruct that image. However, you don't know what it is a lot of the time that you're looking for. But one could say like certain types of like a lung scan and things like that versus a cardiac scan versus a full scan of the whole body looking for metastasis. Though those things have different boundary conditions. But coming up with a general way to do this, I think it would have to be iterative. Do you think? Like you take a quick scan and see what's in there to begin with, and then optimize from that.
That's a basic step to begin with, being iterative.
Okay, let's see. We have another question here. When the rotation angle was limited to 180 degrees, why did the fan beam reconstruction show streaks and missing parts instead of just being blurry? So let's go back. Where is your, we had one where your result where you had 180 degree. Is it here?
I think it's in the summary slide. Yeah.
It's on the summary. Let's go back to that. Here. Can you explain how this, what the sampling was for this and this in detail?
Yeah, so when we limit the fan beam rotation to 180 degrees, like we don't capture the object from all directions. So instead of the image just being blurry, we actually lose entire directional information. The reconstruction algorithm tries to fill in what it doesn't have, and that shows up as streaks along the directions where the data is missing. So basically, blurring happens when detail is low. Streak happens when whole angles of information are missing. And in a 180 degrees fan beam, we're missing angles, so we get those streaks.
And so this is just undersampled. This is, you're just missing angles, right?
Yep, that's right.
Yeah. And do you guys recall how many angles you are required to obtain if you have a fan beam?
360. 360.
Close, but no, you don't need all 360. Remember, so if you basically you need, remember you're collecting data, and when you look in the sinogram space, it is the parallel sinogram space just tilted, right? And so when you say, I need to fill up my sinogram space, when you look, if you do 180 degrees, you have this tilted set of measurements. And at the bottom triangle and the top triangles, there's missing measurements, right? So you've just missed some stuff in a 180 degree sinogram that you would get with a parallel beam. And so you have to overscan with the fan beam, and it turns out that that overscan that's required is the fan angle. So you basically have to do 180 degrees plus the fan angle, and then you'll have enough data to reconstruct the whole picture without missing data. Okay, let's see if there's another.
Can I ask a quick question?
Yeah, sure.
Yeah, on slide 12, where you do the parallel beam reconstruction, there's a discussion of you're seeing of, you know, streak and residual blur. Can you describe what you mean? Because I don't really see any streaking and blurring in that difference image. So maybe the group could expand a little bit on what you meant by that.
Can you
Yeah,
give me
that's right there. Yeah.
which
Oh,
one? This one?
you were right on it. You were there.
Oh,
It was,
sorry, this one?
yeah, yeah.
Okay,
If I look at the difference image, all I really see is high frequency structures, right?
right.
So can the group just tell me a little bit about why you expect to see those high frequency structures, and is that what you're classifying as streak and residual blur?
No, okay. We were actually expecting to see residual blur here because the kind of functions we use in MATLAB was not the entirely practical functions that we use. We actually use the like the version 1 of MATLAB, which usually simulated in very, very easy case. But even if you see in there, I think the mean root square is not that low enough when it is compared to the Chaplogin phantom image. And the residual blur usually happens when the filtering function that we add, like the Ramlack filter, where in the frequency domain, when we add it, it usually overexpresses the high frequency regions and compresses the low frequency regions, which the high frequency regions are those which especially happen in the corner regions of the slice which we are going through. And if that doesn't work well, even the inverse Fourier transform would be affected, and which leads to the residual blurring. But we couldn't ideally simulate those. But yeah, when the parallel beam rays are hitting, majority of the rays are actually wasted because only a fraction of it are going through the slices, which is what is improved in fan beam, where a divergent X-ray, let's say if 10 rays are passing, at least like 7 or 6 are passing through the slice, but in parallel beam, it's not the case, which is why we expect a lot of blurring and artifacts. But yeah, in this case, we couldn't actually simulate the ideal condition by using the functions which we did.
So do you think your filtered back projected image had higher frequencies than the original, or the vice versa? Like when you did this difference, who had the high frequencies?
The high frequencies was actually the back projected image.
This guy. This
Yeah.
guy's sharper. So it's
Yeah.
basically putting it through this iRadon loop sharpens the image up.
Yes, yes.
I see.
Yeah.
Okay, cool. We're going to move on to our next group. Thanks very much, guys. That was great. Go back here. So it's group 23. And here's your summary slide. Okay.
Okay. Hi everyone. Our project compares two classical city reconstruction methods, convolution back projection and inverse Fourier reconstruction. In CBP, reconstruction is done directly in spatial domain. Each projection is first filtered in one dimension using kernels such as Ramlack, which act as high-pass filters to sharpen edges and correct for low-frequency blurring. Then the filtered projection are back projected over all angles to reconstruct the image. IFR, in contrast, works entirely in the frequency domain and is based on central slice theorem. We 1D FFT each projection, map polar samples into an oversampled Cartesian K-space, perform weighted scattered interpolation with balanced density compensation, apply light spectral apodization, Gaussian sigma equals 0.6 and Kaiser beta equals 3, and the Hermitian summarization, then take a 2D IFFT to produce the slice. Our findings show that CBP performs better with few view data, while IFR yields smoother reconstruction, better edge fidelity, and fewer noise artifacts. In short, CBP is faster and analytical but noise sensitive, whereas IFR is slower yet produces superior quality and stability. Thank you for listening.
Okay, thanks. Let me get some quick. Tom, do you have any questions off the bat?
Yeah, I could start off. So nice presentation. I think the presentation went pretty fast over the IFR reconstruction and the code. You actually make a lot of choices in terms of like the gridding and the density compensation. So can you describe a little more detail what gridding kernel you use and how you did the density compensation?
Yes, I can answer that. Can you hear me out?
Yes, we can
Okay.
hear you.
Yeah, we
Okay,
can.
so it's we use the balanced um, density compensation so that it's just like assign a weight for each polar coordinates when we're doing the polar coordinates to the Cartesian coordinates, and we are just tuning the values with experience, just trying to see which one gives better results. So before we do the density compensation, like the stage 4 to stage 5 will give like uh distortions of the image. It's like all the angle is messed up so that we thinking is the polar coordinate converting to the second Fourier transfer to having some issue in there so that we looked up for some ways to do the like weighting to how to weight different values for each pixels. And that's how we do the density compensation.
Okay, and the initial gridding was done. You just use, I guess, the ND grid command. Is that
Yeah.
okay? And then you remove duplicate k-space coordinates. And then can you tell me a little bit about why you found you needed to apply the Kaiser window and also what were the issues with the Hermitian symmetry in your reconstruction?
Yes. So it's like it's giving shadows so that we're thinking maybe like doing that symmetry or Kaiser windows will reduce that kind of shadow. It's also giving a like blurry at the center that we're thinking maybe it's like too much weight in the center. So we want to use Kaiser windows to like reduce that kind of blurry or ghost.
How did you apply the Kaiser window? You applied it in the Fourier space?
No, I think we did in the uh I think it's the second order before the Cartesian ones.
So is it on this? These are the stages, right?
Yes.
Okay. So we come here, you get your projections here. Then you've this is a Cartesian space with the projections mapped
Yes.
polarly, but not weighted yet.
Yeah.
Or is this weighted?
Uh, stage 3. I think we waited at stage 4
Okay.
to bring back all the image to stage 5.
Okay. And when so if we look at these results here, so we have original, this is just naive back projection. This is your IFR reconstruction. What is this? This is the CP.
This is the CBP ones. We forgot to like compare them in the MATLAB window so that we just copy where we previous simulation and just paste into this. But this is the CBP with RAM lag filter.
With Ramlock, and there's noise on here, right? So like
Yeah.
there's random noise, and was that added
Oh,
somewhere in the whole process?
it's can you go back to the or CBP slides?
Uh,
Yes, in here. Yes, this. So before the sonogram, we tend to want to add some noise sonogram to simulate a real application of CPP. So that's why we should really do one RAM lag CPP without filter noise, because when we research the RAM lag filter, it's emphasizing the high frequency data, so it also amplifies the noise. So that's
mhm.
why we want to bring out noise into a real application.
So when if we go to the comparison we have here, there's no noise on this IFR data.
Yeah, we didn't put noise because
Didn't
we're
put that.
having a hard time to do the stage 3 and stage 4 and stage 5 image conversion.
Got it.
We just went through all the concept of the algorithm.
Okay. So there was never a pause here and say, okay, now we put in the noise and see if it comes out to compare it with, say, this noise, signal to noise versus this. Okay.
Yep.
Okay, great. Let me see if there's questions from the gang. Do- I'm sorry, which group are you guys?
23, group 23.
20, thanks. Okay, we looked at that one. Okay, we mentioned that. Yeah, I think we hit all these. Okay, so I was wondering if there can be some kind of quantitative check to show whether the smoothing technique that were showed reduces the detail of contrast compared with the filtered convolution back projection. So looking at, I think they wanted to see or ask you, like, if you were to answer the question, is this smoothed compared to this? Like, what kind of function would you feed it into to answer that question or quantify that?
So, for the MATLAB simulations, we didn't make a quite fair comparison
Okay.
because, like, for the CPP, it's requiring less view compared to FR. For the FR, it's kind of like in high quality, but we having 360 views. We are like 0.5 degrees for each. So I think we are trying to present the best result of both methods that
Mm-hmm.
can produce. But if you put into like they are in the same uh, coefficient or just like same number of views, CPP will be having a better results since it requires less views and less samplings. The LFR requires more calculations and more samplings,
It requires more sampling.
like the views, I mean.
Okay, so you need
Yes.
more views to do IFR than you do CPP. Are you just talking like the this isn't parallel versus fan or anything. This is just where everybody's doing the same.
Yeah.
It's right. Okay. Do you agree with that statement, Tom? Are more views required to do IFR? I don't know. Is that true?
I don't think so, but it depends on how they've done their IFR. So I think,
Uh,
I mean, I do give you guys credit. I mean, it looks like you went through pretty hard and tweaked a lot of things. And I do notice you removed a bunch of data from your IFR, so duplicate things. And so it may just be that how you did it required more data. So
I see.
without going into the details, I don't know. But the information is there, so you shouldn't need more information.
I don't think so. Yeah. I think just the basic principle now in doing the IFR, when you do your interpolation and your raw data and stuff like that, you may introduce some kind of corruption, smoothing, when you interpolate and stuff like that. But I think the amount of data you need is the same. How the signal to noise comes out on both is an interesting question, right? If you
Yeah.
added noise to both data sets and then asked the question like, does one behave better, like in terms of signal to noise? Because it certainly looks like when you're losing a lot of signal to noise in these low contrast features in the middle here on CPP. Okay, great. Thanks, Nick. Well, we're going to move on now, and we're going. Here we are. Sorry. Group 6. Get your example. Oh, there's a lot of info on here. Okay,
Excuse me, Professor.
take it
Uh,
away.
excuse me.
Yes.
Could we share our own slides, like summer slides, because we slightly updated it?
Yeah, sure. I mean, let me see. So I'll
I
just
also I believe sorry to kind of cut in. I believe I sent it to you through your email this morning as well. If you wanted to still represent and pull it up through there, but either way is fine.
I can stop sharing. If you can grab sharing right away, then we can do it that way. Okay, so I've stopped sharing. Well, there was a lot on that slide. I don't know. I hope you didn't add more. Oh, you know what? Wait a second. Let me make sure I can give you permission. Yeah, simultaneously advanced sharing options, multiple participants. Yeah, should be good. Any success? Not so
Yeah,
far.
are you pulling it up by chance, Young?
Oh, okay. I'm pulling it up though.
Yeah, that's what we're waiting for.
Okay. All right. Oops, sorry, there was an issue.
All right, we're gonna give you a 15-second countdown, and we're gonna go back to where we were. There you go.
Shadi, do you want to
Okay.
start?
Yeah, I can go ahead and get started. Okay. Yeah, we're group 6, and in our presentation, we compared CT scan geometries and focused specifically on why modern scanners use fan beam geometry. So in the bottom left image, you can see the advantages in the evolution of fan beam CT, where in the first generation, it was used with a pencil beam with a translate then rotate motion, which ended up being very slow and limited. The second generation ended up widening the beam slightly, allowing for faster coverage. The third generation introduced a rotating X-ray source and a curved detector array. And subsequently, the fourth generation added stationary detector rings with only the source rotating, which made scans dramatically faster. On the right hand side, we additionally dived briefly into reconstruction algorithms. Parallel beam CT gives simple linear reconstruction, but requires translate, rotate, then rotate motion, whereas fan beam design captures diverging rays with a rotate-only scan, making it quite faster in practice. That speed, however, introduces two core challenges, namely incompatible sinogram coordinates and non-uniform spatial sampling, basically where the rays spread out omnidirectionally such that sampling density changes across the field. We presented fan beam reconstruction formulas and showed that these problems are solved either by rebinning fan data into parallel sinograms or by using a dedicated fan beam filtered back projection that applies a correction weight, for example, a cosine gamma term or distance-based factor during back projection. We also compared sinograms and ran realistic simulations to demonstrate image fidelity trade-offs. And if anybody has from my group any other things to say, if not, we're happy to field any questions you may have. Thank you.
Okay, if you want to stop sharing, hand the screen back, we can start from there. All right. Now I'm gonna. Okay. Let's go here. This is. Are we here? No, we're here. Okay. Great. So I guess let's get to your results here. Oh, this was an interesting slide. A lot of the questions that came up were in the context of this uneven sampling as a function of gamma, right? Or the spread of the sampling is gamma. And in the video, I was looking forward to you explaining what the heck's going on here because it looked very informative, but it kind of flew by. Can somebody explain this graphic? Let me zoom it up. It looks useful. Anyone want to jump in?
Uh, for my opinion and understanding is like when we do the same beam, the energy will like constrict in the middle. So except for the edge side, the energy will decrease. So we need to have some weighting to make it like more uniform. That's what I thought.
Okay, so
Yeah.
can you tell me what's going on in this versus this? This this is your source, I'm assuming. Did you guys make this
Yeah.
paper? Or
No, I just do some literature review, and this is for another paper talking
oh,
about the fan beam and the and the original one's difference. Yeah.
okay. So hence why when I started the introduction, you always want to put the citation down there where it came from, right? So that there isn't a confusion that, oh, they've made this really cool diagram.
Oh, okay. We put in the last page for the slide. Yeah. Sorry,
Okay.
I will put in it down. Yeah.
Okay, great. Just where the drawing is, you can just either a link or anything down there that says here's where you would find it. So anyway, so this is the density of photons or the flux as a function of position on a curved detector, and this is on a flat detector. Is that correct?
Yeah.
I see. I see. And then so so basically you have two different functions. They both have a different sort of photon flux as a function of position on the detector, but that function is just different. This is that what this is saying?
Yes.
I see. Okay, great.
Yeah.
And when you guys are looking at fan beam, we're talking about this thing here, right?
Yes. Yes.
All right. Cool. So let's get to some questions. Do you have a question, Tom?
Yeah, can you go to just a clarifying question, the slide, I think it's 11 says compare the sinograms.
Um,
It's right before the summary.
right
Slide
before.
11.
Slide 11, yeah, it's towards the end.
Oh,
I think
511.
Slide 11.
Oh, slide 11.
I
Sorry.
think it's for the next two page. Next is like very button.
Almost at the end.
Oh, okay.
Yeah, yeah.
There,
Next two page. And
Keep going. Right before the last slide.
okay.
Oh, I see.
know what?
This is the presentation that, oh, there we go. Okay. Here we
Yeah,
go.
there you go.
The presentation that the slides cut out.
They did. Yeah, guys, this is why you gotta proof it because the last part of your presentation looked like this.
Yeah.
Right, so
oh,
just
a more realistic simulation provided in source file.
so it was just this. So we had to go to your source files and everything to figure out what the heck was going on.
Yeah, so let me just ask the question so because you guys can see the slides. So I see on that slide 11, the top two things look like corresponds to your Python code, which is just some sinograms. And then on the bottom, you've got more realistic simulation referring to reference 5 and more realistic simulation referring to reference 4. So just clarification, yeah, that's the one right there. So are these more realistic simulations? Do you guys do those, or are these just screenshots from the those references?
These are screenshots from the references. Yeah, we just thought it would be more realistic because the researchers added like more noise and more like practical parameters than a simple like a back projection. Yeah.
Okay, and then the top two are you're just simulating for 3-point objects. That's their Python code that you provided, right?
Yes, yes.
Okay, great, thanks.
What are the breaks in it? Like it just stops here. What's going on there?
Oh, so for some like so the source angle, the range of the source angle not necessarily overlap with the detector angle. So there might be some non-overlapping between the ranges. If you tweak around the parameters, it will change like the beta and the gamma. So sometimes it will give you some like a breakage, or sometimes it will give you a nearly perfect like a sinogram. Yeah.
Okay. And the sinograms on the right are for the same object as on the left. They're just using the fan beam. That's
Yes.
all I did. Okay. Okay. All right, where are we? We're at 54. Oh, we got to move on. We got two more folks. Well, thanks for the presentation. And again, check next project. Just do 4x, or just drag the damn thing along like this and say, oh yeah, every slide's in there. It looks good. The other thing
Yeah,
is,
I sorry to cut you off. Yeah, I really apologize for that. I think that was we did realize that. I was kind of editing, some parts and making sure it was good. I guess I just uploaded the link that was the old version and not the new version. I really apologize for that. We did notice this. I just completely did not even double check it after I uploaded it to upload the right one instead of the older version. So I apologize for that.
okay, no problem. Um, what was the other thing? Oh yeah, a few of the presentations had pretty rough audio. So that's the other thing. If you preview it, and I know you each do it on your own computer. Some people's computer, I don't want to highlight Windows in any way, but a lot of Windows computers have crappy audio, right? And so it's really hard, you're focusing, trying to figure out what the heck's going on. So just get on a computer that has nice audio is another thing. Okay, here we go. How filter selection affects noise and diagnostic accuracy. And so we'll go here to a summary. This is group 15. And here we go. Yeah, this was interesting. I didn't. Okay. Can you see everything on that slide? Do I need to maybe make it a little smaller so you can see it? Okay, take it away. Oh, sorry. My bad.
Oh,
There we go.
okay. Hi everyone, we're group 15 and our project focuses on how filter selection affects noise and diagnostic accuracy in CT imaging. So we simulated CT reconstruction using MRI data of 24 mice by applying the radon transform, and then we rebuilt those images using inverse radon with 3 different filters, the Ramlack, Shep-Logan, and Hamming. And visually, we saw that the Ramlack filter preserved the most high frequency information, so it produced the sharpest edges, but it also amplifies noise the most. The Shep-Logan filter reduced some of that high frequency noise, which gave us a balanced trade-off between detail and smoothness. And the Hamming filter contributed to the most amount of smoothing, which created the lowest noise images, but it also created softer edges and more blurring. And we quantified these differences using the signal to noise ratio, contrast to noise ratio, and the edge width measurements. And the results matched what we saw visually. So Ramlack had the lowest SNR and CNR with the narrowest edge width, and Shep-Logan had mid-range values, and Hamming had the highest SNR and CNR with the widest edges. So overall, we see that increasing the smoothness can improve the SNR and CNR, but that reduces spatial resolution, which is consistent with what we see in CT practice.
Okay. Tom, do you have any questions right out of the box there?
Yeah, I had a quick question about slide 11, quantitative evaluation of filter performance. Just a clarifying question. So in your slide, you say for the Hamming window, it has the widest edges or the strongest smoothing. But in the table, it looks like the edge width is 35, which is the smallest edge width. So could you just clarify what you mean by that? And I just didn't quite see how that matched with what the summary statement was saying or what you were saying in the video.
That may have just been a writing error on our part. But I can quickly explain how we did edge width one more time. It's measuring how quickly in pixels we transition from the dark to bright areas across a boundary. And so that was from like the 10% to the 90% of maximum intensity on the edge spread curve. So if we, I don't know, we might have just written down the wrong thing,
Well,
but
the graph
the data
also
should be
shows
correct.
it's the lowest. The graph also show it's the lowest edge width. So your bar graph shows it. The Hamming window has the smallest edge width.
Yeah, I think it must be a typo, right? Because you've got the Hamming with an edge width of 35 and the Romlock with an edge width of 44. That's backwards, right?
Right, yeah.
The width would go wider with
Yeah, smaller edge width is a sharper image, so it must have just been error. Sorry.
Okay, I just want to verify that that's what you meant, that you expect it to be a larger edge width for Hamming.
yeah. Okay.
Yes.
Okay.
And when you like measuring edge width in images is fraught with problems, right? Because you don't know if it's an actual sharp edge or not, and things like that. But for a comparison like this, if you're on the same spot, then it's probably okay. And this is essentially just the same data pushed through different filters. So you should be able to compare things and have it. But as you can see with your variability of the edge width, right? It's pretty huge. What does this variability come from? So you're saying I've measured my edge width, I get 44 pixels is our unit here, gets me to halfway down from 10% down to 50% or something.
Um, yeah, so it's 10% to 90%. The issue we
Oh, that's the
realized,
whole way.
yeah, we realized this issue maybe a little bit later on, but these images were all taken in the exact same layout. So it should be just be a bunch of different mice images set up about the same way. But the lines were drawn on one example picture. Maybe that was just the top picture on the stack. And so we assumed that the like between the different images, there wouldn't be too much movement, except for when you're drawing something so small as an edge width. I think we picked somewhere it was around the eyeball that we drew that line.
Yeah.
If something shifts around, then you could get, you didn't overlap that edge, or
Yeah.
maybe it was slightly crooked and not perpendicular. So that was um, something on our end that we should have checked more. We just didn't know a better way to do it with so many images. We didn't um,
Yeah.
like have time to go through all 94 or 96 images and draw that line 96 times. So that was just our way of simplifying it.
So when you need to go through 96 images, the best way to do it is to write a little bit of Python code that makes like a GIF loop or a movie, and you just like just watch the movie, and you can see, like, is my assumption that this I'm marking an edge, that edge in the 96 is the same, and you just like play them, and you can tell in 10 seconds if it's the same, right? The other interesting thing here, though, for me is like you took MR data, right? And made, with a radon transform, you projected that MR data. That's correct, right? That's what happened.
Yes.
Yes. Okay. One, why did you pick MR data? Why didn't you pick some CT data? What's the difference between MR data and CT data this is a rat head or a mouse head or something? All right.
Yeah, it's a mice head.
Mouse head. Okay. What would be the major difference in those two data sets? If these are CT scans, would they look like this? They would not, right? You'd
Yeah.
have massive signal from all of the bone, right? And things like that. So this is a very interesting data set. I'm not saying it's a bad way to look at the difference between Romlock, Shep, Logan, and Hamming. In fact, maybe it is a good way to look because it has more subtle contrast than CT, right? The other question is like, what is the noise? Where's the noise coming from? You do signal to noise, contrast to noise. What is the source of noise? Did you control it at all or just so the MR images themselves, when you look at the MR picture, the original picture, it obviously has noise on it, right?
Yes. Yeah.
So, and you guys didn't, once you made the projections with radon and you had your sinograms, you didn't futz with the noise after that?
Um,
You just
Not
left.
really. The only thing that we really did with we did a frequency cutoff at 0.8,
Mm-hmm.
and that's because we noticed that 1.0 we were passing all of the frequencies, so all of the images looked really sharp and noisy, and so the filters are behaving pretty much the same. You couldn't really tell. But then dropping it to 0.8 trimmed sort of those high-end frequencies. And so we just felt like that gave smoother and more realistic CT-like noise while still keeping enough detail to see the differences between the three filters.
Right. So my comment on this, and anyone else can chime in if they want, but is that all of those pictures look really similar, right? Like I'm surprised at how similar. And so
Yeah.
if you're demonstrating a difference, specifically a signal to noise, you might want to like go to a place that has dynamic range to see that difference, right? So this data obviously has pretty low noise because the realm lock filter, when you bring it back, there isn't a heck of a lot of noise on it. Normally you would see like it would be like looking through hash on a TV screen or whatever, right? And you don't know what a TV screen, but it would be randomized pixel noise. And so you might want to add noise. Like once you take the radon data, now you've got your pseudo sinograms, they're MR sinograms, right? You might want to add noise to that to make these pictures more illustrative of how the filters deal with the noise.
Yeah. Yeah, that definitely makes sense. I think part of it too is also putting it together into one figure just makes them really small, just to show them side by side. When I was doing all of this coding on my laptop and
Yeah.
having them blown up full screen and then, closing one window, seeing the other, it was a little bit more obvious, but I agree we should have maybe added some noise.
Yeah. Yeah,
I
these
had
pictures are similar.
okay. I had a clarifying question. So it looked like when I was watching the video, the noise for the noise region, let me annotate. I think you guys were picking like this as a noise region. Is that right?
In the
I
video,
think I might have called it the noise region, but it was just an optional sort of second sampling of a uniform region inside
Okay.
the
So what
head.
did you actually pick as your noise region then?
is it here? So that's the sample.
Uh,
So I think that's their signal.
Yeah.
And then
Oh, I might have missed the noise. We're drawing a box up here. Is this going to be the noise region?
that's their background.
Oh, yeah.
Then I think if you go beyond that, there's a noise region if you go to a further slide. Keep going, keep going, keep going, keep going. Yeah, I think it's starting here. See noise.
There
Yeah.
we go. Okay. So that's noise.
Yeah. So just so you know, I mean, in the actual for the MRI image, that's still tissue, right? I mean, that's actually part of the mouse head or body. So were you the group? I think so, Ellie. Just so you know, there was a group that came and asked me afterwards that they'd already done MRI images for their CT project, and since they were done that, I said it was okay if they were just looking at the effects of the filtering and stuff.
Yeah.
Are you that group? Just to clarify.
yeah, we came in during
Yeah.
office hours.
Okay, okay, yeah. So just so Dr. McVeigh knows. So yeah, so just think for also just as you're because these are MR images, what a noise, I mean, this would not actually even be an MR, this would not be a noise region for the MR image either, because that is an area where there is tissue.
Got it. Okay. So I think we should have picked the background area outside of the object as our noise.
Yeah, for
Um,
MR, yeah, definitely.
yeah.
Yeah.
In
And just to
MR,
explain like, oh,
yeah.
sorry.
Yeah, in MR, air is a good place for noise. Usually, sometimes there's ghosts and all this other junk that's in the air, but you can sort of focus down and take a look.
Yeah, I also just wanted to explain the green circle. It was actually the radon transform that made it a little bit tricky.
Yes.
because the edges of the reconstructed images become, distorted or uneven. And
Hmm.
so in order to keep things accurate, I sort of just drew that as a guide so that we wouldn't be using bad data, essentially.
Yeah. So sometimes you can also take your original image that you're going to use to make radon data and just pad it, right? So you put something sensible out there like air, right? And then you project that, and so you get it more of a sort of window there. Okay,
Got it.
thanks. I think we get it. And if you want smooth images, use Hamming. Okay, we're down to one more. We got to get going here. And this is dose um, calculations, right? Yeah, estimating radiation dose. So let me bring up this is us. Okay, take her away.
Yeah, hi. So we basically looked at the different methods to estimate radiation dose. Specifically, we focus on chest CT scans. So CT scans are a very common diagnostic tool. They're very common and useful diagnostic tool, but they do expose patients to a level of radiation. And this can be important because some populations are more vulnerable to radiation than others. So it is important to sort of quantify how much radiation a patient is being exposed to. So we first looked at current standard methods to compare radiation between different machines. This involves using an acrylic 32 or 16 centimeter acrylic phantom. And through this, you get values such as CTD, DLP, and SSDE. So these are basically standardized values that don't really give any patient-specific or organ-specific information, but they're more useful in comparing different machines or different settings. Uh, so they estimate radiation but provide no information regarding organ or tissue specific exposure. They do take into account things such as different body parts or, for example, patient size and the SSDE value, but you don't get like a number for patient specific radiation dose. So one way to do that is not with standardized phantoms, but with something called the Monte Carlo simulation, which provides physics-based organ-specific estimate of radiation dose. So we did a sort of basic Monte Carlo simulation using MATLAB. We used data we found online for a chest CT scan. And what we did essentially was approximate the volume using data files. And then we segmented tissues based on the different Hounsfield units. And this created an attenuation map to assign density and mass attenuation for each tissue type. And then we use radon and iRadon to basically forward project along 18 slices in 10-degree increments, calculate the energy absorbed at each step, and then back project to distribute the absorbed energy along the paths. And this is a very coarse sort of rough Monte Carlo diagram, but it gives you a general idea of how it works.
Okay. I I have one quick question. I was confused in your presentation by the images that were this is labeled bone mask, but it I don't really see this as a mask. And perhaps you can explain the intensity of the pixels in here and what they represent.
Yeah, so I can take that.
Okay.
We basically tried to explain how much radiation each organ was absorbing. So ideally, a bone should be absorbing higher radiation as compared to soft tissues and heart.
Yeah.
But so the code that we put on MATLAB was from scratch. We tried to do it, but coding didn't come naturally to all three of us. So, and the data set also that we were using was not very versatile. So the image that we got back was quite generic, I would say. It was not very accurate, to put it bluntly.
Yeah. Okay. All right. So basically this was the image returned by your software that went in to find all the
Right.
using Hounsfield units, and it came back as a binary picture I'm assuming the white pixels are 1 and the dark pixels are 0. And that's how a mask works, right? You have like a decision that is, but it just got it wrong, is what we're looking at.
Yeah, correct.
Okay.
And we tried to resolve that, but we didn't know any better way to do it.
Yeah, I see. I see. And so that explains like here's the bone mask, the mu mask, and and these are all 1 or they're all the same value or something. Okay. All right. Cool. Tom, you have
I also kind of wanted to comment on that. This is a great slide for that, but this is a simplified model. So obviously there's more tissues represented in this scan, but we did just kind of take the basic like lung tissue, which is obviously less dense because it's filled with air, soft tissues, and then denser bone tissues. And we segmented by that with the Hounsfield units, which you can see on the slide here. So that is another reason. This is a very basic model, like we had said.
Okay. I'm still not clear to me that the mask represents what you want, but that's debugging and messing around with the code to trying to get it to work.
I had a question about that slide you were just on there.
This guy here, yeah.
So you're talking about the dose being highest in bone and then greater than soft, but the bar graph, if it looks like the bar graph, everything looks the same. Was there a mistake in the bar graph, or is it just they're really close, the doses, or?
I can take that. So it was our data set that we used. It was not very versatile. So ideally, if you were to put in multiple data sets with a lot of different tissues, the bone would probably have the highest one because it's absorbing a lot of dose. But because our data set was not very versatile, so it came out pretty even. But we still let this bar graph be on the slide because we just wanted to show that if we were to use multiple data sets, then there would be a lot of variation occurring in the bar graph.
Okay. And I just want to clarify, so although you do talk about Monte Carlo simulations in the video, the actual code doesn't do any Monte Carlo simulations, is that correct?
We definitely attempted to do a Monte Carlo simulation in a 1D scenario, which obviously isn't also fully encompassing because these are obviously 3D scans in a 3D process. But we tried to forward project it along our 18 slices, which again, this is very coarse, so that also doesn't yield great data. And then the Monte Carlo part was calculating like the energy absorbed at each step along those projections. And then we back projected it, which is the image you see on the right, to distribute those energies across the paths that we chose.
Okay, thanks.
So some of the questions that came in for this. Okay, so with new technologies like AI-based iterative reconstruction, so we're talking about, reconstruction methods that will reduce the amount of radiation necessary. So how is the traditional relationship between MAS, image noise, and patient dose being changed by, this new generation of low dose recons? Do these advancements challenge? This is the question for you guys. Do these advancements, I'm sorry, challenge the ongoing relevance of the CTDI vol and DLP paradigms explained in your video? So forgetting about your results, just the whole reason to calculate CTDI vol and DLP, is that modified in any way by these new low dose reconstruction techniques?
Yeah, I can answer that. I can't fully comment on if those will be modified. They may, so those methods do depend on like a conversion factor, the K value and an F value that depends on calculating like the water equivalent diameter and so forth. So those methods may be improved through AI, definitely. And in terms of if those are still relevant, I do think they would definitely still be relevant, even if we can in the future one day get perfect patient specific dose values, because right now they're really often used to just compare machines, one, and then also to make sure that there's daily quality checks and validation checks that are done on the machines. So for that reason, they would still be very much used even with the advancements.
Okay, so as low as the dose can go, I mean, you still need photons to make pictures, right? So as low as it's going to go, the CTDI vol and DLP still makes sense.
Yeah, and it just make sure that a machine isn't like somehow tripling the dose one day, and it's a good way to check things like that.
Okay, all right. Let's see if we have one more question for you guys from the gang.
Am I allowed to ask a question of the professors?
Yeah, sure. Go.
I never thought about it during the lecture, but when we have the fan beam, like radial imaging,
Yeah.
would the central point that gets exposed to the most radiation, is there studies that looks at that specific area? Like, is there cell death or any sort of higher risk of cancer at that specific little focal point?
That's an interesting question. And when you do, let's go to radiation therapy, where sometimes you use very high energy X-rays, higher than 120 kVp, up to MeV X-rays, and they come in very narrow beams. And if you have a tumor, say on the top of a kidney, right, and that thing is a centimeter and a half ball, you can hit it with all of these beams that are, it's on a gantry and it just shoots the X-rays through that point, the center of that tumor, and then shoots it from a different angle and a different angle and a different angle. So what you're doing is you are amplifying what you are saying right now. It's just like there will be a spot that has much, much higher dose just because of the geometry, right? And in radiation therapy, you design the geometry to do that. In CT, it's interesting. It doesn't work out that way. And the reason is the periphery of the person, if you do nothing, the periphery outside on the fan beam gets a lot of X-rays compared to the middle because the X-rays get absorbed as the beam goes through the patient. So the deeper you go into the patient, the more absorption that's occurred, right? And so usually what you do is you put on a bow tie filter, which we talked about very briefly, where you attenuate the stuff on the outsides of the field of view so that the edges don't get overdosed for usually stuff you don't want to image anyway. But you need it there such that you project through it in some angles. And so you put this filter, it's called a bow tie filter, that lets radiation through the center and attenuates it out at the edges.
Gotcha. Thank you.
Yep. Okay. I think we're good there. Thanks very much for everybody for putting a lot of effort into making the projects fun to watch, right? And for uploading your code and your slides and everything like that. And the questions are really good. Because of time, we didn't get to all the questions that came in. So thanks for participating in that way. And we will pick it up on Wednesday morning with, I guess, either 6 or 7 more groups, right? Okay.
Thank you.